Next time you're driving, look down at your dashboard and ask yourself, speedometer can measure karta, speed or velocity? In everyday conversation, we tend to use those words interchangeably. In physics, they describe entirely different properties of motion. Speed is a scalar quantity. That means it only has a magnitude, a standalone number telling you exactly how fast an object is moving. Velocity is a vector quantity. It requires that same magnitude plus a specific direction. Think about it like this. Can your speed be 0? Yes, but only if your car is completely parked and not covering any distance. But what about average velocity? Could your average velocity be 0 even if you just drove 100 miles down the highway? The answer is yes. Knowing how fast something moves gives you an incomplete picture. Unless you account for the exact shape of the path it takes through space, that single number on your dashboard is hiding the reality of the vehicle's motion. This diagram breaks down the formulas. Average speed is distance divided by time. Average velocity relies on total displacement. As the straight red arrows highlight, displacement is a direct vector from point A to point B, regardless of the journey's winding path. So average velocity 0 cup, it happens when you make a perfect round trip. If you pull out of your driveway and drive around the city for 2 hours and eventually park in that exact same spot, your total displacement is 0. When you divide 0 displacement by the time of the trip, the math forces your average velocity to be exactly 0. Average velocity evaluates the net change in reality. It ignores all the physical miles covered and the fuel burn to complete the journey. This brings us to a specific paradox. Circular motion may change a thigh. Let's say a car is driving along a perfectly circular track and the speedometer is locked at exactly 60 miles per hour. The car's speed, the magnitude, is perfectly constant. But because the track is curved, the direction the car points shifts with every inch it moves forward. Because the direction vector is continuously altering its angle, the overall velocity is also continuously changing. This means the car is mathematically accelerating at every single moment, even though it never speeds up or slows down. A curved path continuously alters the physical state of a moving object. Measuring speed alone is blind to how objects actually move in three-dimensional space. Up to this point, we've been looking at macroscopic averages, spanning entire road trips and laps around a track. We can also zoom in to calculate the motion of a single frozen moment. This is a position versus time graph. Normally, to calculate an average velocity, we pick 2 separate points on this curve and draw a line between them. To find instantaneous velocity, we use a mathematical concept called a limit. We take the time interval between those 2 points and shrink it down toward a mathematical 0. As the points merge, the connecting line flattens to rest directly on the curve, becoming a tangent line. The steepness or slope of that tangent line reveals the exact velocity for that specific frozen instant. Instantaneous velocity bridges the gap between a geometric journey spanning hours and the actual physical reality occurring in a fraction of a second. We can now answer our opening question. When you look down at the needle on your dashboard, it is only measuring your instantaneous speed. A GPS system tracks both your exact rate of travel and your geographic heading simultaneously. It measures your instantaneous velocity. Speed is a simple rate of distance consumed over time. Velocity describes a complete physical state. It maps your rate of travel alongside your